My name is Jackson Stevens, I'm part of DS Math, and the title of my project is The Correlation Between Radar Cross-Section and Aircraft Design. The inspiration for this project comes from a couple different places. The biggest source of inspiration for this project is the fact that I want to be an aerospace engineer. Part of an AE's job, should they decide to work in defense, is to design airframes that are capable of flight but are also able to reduce the plane's noticeability to ground-based radar systems. I wanted to get a head start on my education, and I felt this was an appropriate way to do that. Another source of inspiration is simply curiosity. I've always been interested in radar and how planes are designed to defeat it, and I took the opportunity to learn more. The research question I chose to answer is a plane that is invisible to radar possible? And the way I went about finding the answer to this question was research, mainly because 18-year-olds aren't allowed to build and fly their own fighter jets for some reason. I scoured the web for information that would help me find the answer to my question, and I think I was largely successful in doing that. My research revealed four main characteristics that affect an aircraft's RCS, or radar cross-section, a measure of how big a plane shows up on a radar. The smaller the RCS, the more invisible your plane is to radar. The most important thing to know is how radar works. When a radar beam strikes an object, the electrons in the object are shifted ever so slightly and catch the energy from the beam before returning to their original position, throwing the radar energy back out of the surface at the same angle it entered. There are two kinds of radar I'll be dealing with here: search radar and tracking radar. Search radar uses big wavelengths of light to sweep a section of the sky and get a ping back from anything that might be there, like how you use a flashlight to find something in a dark room. Tracking radar, on the other hand, uses pencil-thin beams that track an object's position very accurately, which is why tracking radar is often used with SAM systems, which are surface-to-air missiles. This is like using a laser pointer to keep it fixed on whatever you find in the dark room after you've located it with that flashlight. Essentially, search radar can find stuff but can't track it, while tracking radar is the opposite. It'll track stuff, but it's pretty bad at finding it. This leads to characteristic 1, which is the physical geometry of the plane. Constructing the airframe out of small geometric shapes at various angles of each other is a good way to defeat tracking radar. The F-117 Nighthawk took advantage of this property, as can be seen here. When a tracking radar beam hit it, the beam would be bounced away from the receiver, rendering the plane invisible to tracking radar. Because the geometric shapes are large enough to fit the entire circumference of the tracking radar beam within their area, the plane makes tracking radar useless by bouncing the entire beam away from the receiver. However, because search radar uses such large beams, the plane basically acts as one huge reflector when struck with search radar, meaning that stealth planes aren't really that stealthy. They're just stealthy enough that enemies can't do anything about it. It is theoretically possible to build a plane large enough to defeat search radar, but the plane would be so large that you wouldn't need radar to see it, you could just see it with your eyes. Another thing to note about the F-117 is that due to its highly geometric shape, the builders had to install a state-of-the-art, before its time, fly-by-wire system into the plane to counteract the instability of the plane due to the unnatural way in which air flowed around it. That's a trade-off engineers have to make: stealth versus stability. Next is characteristic 2, the direction of the illuminating radar. Depending on where the radar beams are coming from, the plane will have a different RCS. This means that engineers need to consider all angles when designing a stealth plane. Because changing something on one side of a plane affects the way it's shaped on another side, you need to construct a higher dimensional plane in order for it to really maintain radar invisibility from all directions. So this is a radar cross-section diagram. And the way it works is that the closer the black spikes are to the plane, the worse the RCS is from that side of the plane. So here, the plane is fairly good at defeating radar from the sides and the front, but it's really not that good at it from the back because the black spikes are very close to the back of the plane. The third thing is the frequency of the illuminating radar, which is something I've already talked a lot about. Basically, the narrower the radar beam, the more accurately it tracks things, which is why tracking radar uses those narrower beams. It is more effective to design a plane to defeat this kind of radar than it is to build it so that search radar can't get a hit on it, as building a plane that massive is a waste of money and materials. The analogy used here is that it's kind of like a TV, where search radar is kind of like you're kind of tuning the TV in, but not really, and you can kind of see what's going on, but you're not really sure. So you can tell the plane's there, but you can't get a really good fix on it. And then if you go over the SAM diagram, that's like you've really tuned in the TV to just the right channel, you can see exactly what's happening, which is really good for tracking things and launching missiles at things, but it's really not good for just finding things. The final major component of RCS is the electrical properties of the aircraft surface. If the aircraft is built out of a material that is good at absorbing the energy created by the radar, impacting the electrons on the surface and turning it into heat, the plane will catch the radar and not throw it back, rendering the plane invisible because the radar thinks that the beam just kept going and didn't hit anything. Some surfaces are better at doing this than others, but there are also varying costs and practicality to consider in constructing a supersonic airplane out of certain materials. For example, foam is very good at absorbing energy, but it doesn't hold together very well when it is propelled at speeds above Mach 1. The end result of this research is that building a plane that is completely invisible to radar is not possible without using higher dimensional building methods that we as humans simply cannot comprehend. I did, however, discover a way to make a plane impervious, if you will. Aircraft, no matter how stealthily they are designed, will always be picked up by search radar if the radar wavelength is large enough. They will not, however, always be picked up by tracking radar if the airframe is conducive to defeating the narrow wavelengths it uses through the way its hull is constructed and what it is made of. This means that it is completely feasible to develop a plane that can't defeat search radar, but is very good at defeating tracking radar, with an end result of the enemy knowing that the plane is there but not being able to do anything about it. This is ultimately the goal of stealth planes. Radar is also not the only factor that goes into a plane's overall stealth rating. There are other things like acoustics and infrared and various other ways of detecting planes, but for this project I focused only on radar. Making a plane less perceptible to infrared by building an engine cowling might make it more visible on radar, which is an example of just another trade-off that engineers strive to minimize as much as possible. This project was very interesting to me personally because I plan on getting a job in the aerospace industry, and I felt that understanding how radar worked and what options engineers have to minimize its effects would be a good head start for me before I plunged into the deep end of aircraft design. Learning about radar was very enlightening for me because I understood the concept of emitting light at an object and having it bounce back, but I didn't know the science behind it, with the electrons getting moved around ever so slightly. I found that really interesting because it got me thinking about ways to use that property to absorb the radar more effectively. This project also expanded my knowledge about aircraft design with the case of the F-117 and having to balance radar deflection ability and actual flying ability. It turns out that it's really hard to get a brick to fly through the air with an acceptable amount of stability. This project furthered my interest in the aerospace industry, and I can't wait to learn more about this field in college.